off from yesterday. We didn't quite finish section 3.3. So these are measures of relative standing, and then box plots, which we'll get to, right? So remember, a measure of relative standing is different than the other measures, right? So this whole chapter was on how do you was just descriptive statistics, right? So the first section is how do you describe the center of a set of your data, right? That's pretty easy, mean, median, mode. The second was a little bit harder. It was how do you measure how spread out your data is? There are measures like range and standard deviation and variance. Here, we're talking about measures of relative standing. So a measure of relative standing is not something that applies to the whole set of data. It tells you how one piece of data relates to the whole set, right? So, for example, the z-score. Right? The z-score, right? I always talk about everyone has a height, right? If I can want, right? So if I do calculate the z-scores, right, for all women, American women, right, and I look at Regina's z-score, that will relate to tell us how does her height compare to other American women, right? So the z-score tells you how does this piece of data fit in with the rest of them. So we mentioned this, right? We mentioned that this is the formula for the z-score. The z-score is the great because it just tells you, right? It just tells you how much, it tells you how many standard deviations you are away from the mean, right? So that basically normalizes it, right? This allows that you can understand where something fits within the data without knowing much about the data, right? You quote an alien, your height z-score, and you know it's 2.5, they know that you're very tall, despite the fact that they don't know what the mean height is of a people or how much the height vary among human beings. They've never seen a human before. So the reason why is that data has a pattern, and we'll talk a lot about this soon, or soon-ish, right? That the z-score is between -2 and 2, right? 95% of the data is in that range, right? So if your z-score is less than -2 or more than +2, that's considered a significantly low or significantly high value, respectively. And here are some examples of z-scores we calculated. This is kind of where we ended yesterday, right? So this is some problems of my own. So why don't you guys work on these, right? Just to warm yourselves up to see if you remember how to do the z-score. These are some z-score problems that I had ChatGPT write for you guys. I had to do it a couple times. Every time, it made all of the answers 1. The first like 2 or 3 times I did it. So I don't know why. All right, so everyone understands what they're expected to be doing right now? All right, let's go to town. To give you an idea, you will be calculating z-scores until up to the last day in this class. So this is something important for you to master. All right, let's come together here because I think you've had, sufficient time to do this. So the formula for the z-score is x, and right? It's either minus the mean, right? Which it's either x bar or s, or alternatively, it's mu if it's a population, right? Either way, right? It's not really different formulas, right? Either way, it's data minus mean divided by standard deviation, right? It just depends which type of thing you're talking about, right? All right, so then you just kind of want to identify what's going on in each of these. So what is x, the data piece? So it's always something, right? The x is always referring to an individual, right? Something that does not, I'll get to you in a second about it, does not describe the entire set, right? But one individual. So what is that in this first one? Yes, so that is the weight of the particular dog. And from that, we subtract 0.5, right? Let me just point out another thing, right? So this difference, right? 4.2 is in kilograms, right? And the bottom unit is also in kilograms. So what happens to the units? They cancel out, right? You can see this. That means the z-score is universal regardless of what measurement you are using to, right? Here you're weighing dogs, right? If you used grams, pounds, what else, right? How number at weight and number of jelly beans, right? Still going to give you the same answer, right? Which in this case is 0.875, right? Anyone else get this? Okay, so it's a positive z-score, which means that this is a heavier dog than average, but would this dog be considered significantly heavier than average? No, right? You see this dog walking down the street, right? You're not texting anybody about it, right? All right, so same calculation here. The measurement is well, 120 is the yeah. Also, this uses the word average. I should have been more careful about that. I should have used the word mean. The last one. So 105 is Mary's amount of time to do whatever task this is, right? The average time is 120. And the standard deviation is 15 seconds, right? So notice here, right, be careful because you can't just say, oh, it's bigger minus smaller. Here you should get a negative answer because that means, right, less time than average, right? So that's 15 seconds fewer divided by 15. That's the easiest math here. That's -1, that's z. So you will have z-scores that are negative, which just means this person is faster at completing this task, right? So this is a negative z-score. Make sure you understand what it means and that you can get negative z-scores all the time, right? If you want to type this into your calculator, right, notice like calculators use the division sign that looks like this. So it does not group it, right? This means do that first, the fact that it's on the top of a longer fraction bar, right? You type in your calculator, this is the key, right? And then you use the division key. It's going to give you the wrong answer. Because order of operations, PEMDAS, right? It is division comes before subtraction, right? So what it's doing is it's dividing these two numbers and then subtracting that result from 26, right? So you need to, if you want, I recommend type, so either you need to do this, then divide, or more, I more recommend putting this in parentheses, right? And then doing this, right? If you do your calculation on one line in your calculator, it's easier for you to fix. Questions here on how we got these z-scores. These z-scores just tell us how do they compare, right? What's their standing? What? X, right? Whatever the individual piece of data minus the mean divided by the number of standard deviations. This formula to me is intuitive, right? That top thing's just telling me how much larger or smaller it is than the mean, right? But, you know, it's if you're 1 pound bigger than the mean, is that a big deal? I don't know, right? Is 100 pounds bigger? Maybe. I don't know. It depends what we're measuring, right? So to figure out how big of a deal that absolute difference is, you need to divide by what's the standard difference, which is what standard deviation is. So you're figuring out how many standard deviations fit between the mean and my data piece, right? And with a negative number indicating that those standard deviations are to the left. Any other questions? Now, z-scores is the most commonly one measure of relative standing used in statistics. But when things are being quoted to average everyday people, we don't typically use z-scores. we use something else. Any thought about what that is? So you might have get these when you get a standardized test. These are often used when they weigh a baby or measure their height or and decide, right, like is that a particular, it's okay if it didn't, percentiles, right? So a percentile is a measure of relative standing, right? So for example, right, if you said, right, like on the SAT, I scored in the 85th percentile, that does not mean you got 85% of the questions correct. It means that roughly speaking, you scored higher than 85% of other test takers, right? Roughly speaking, 15% did better than you, 95% did, we're sort of the same, right? We use numbers, right? So P1 means whatever, however many questions the first percentile got, right? So you use these. So P with a subscript of a number between 1 and 100 tells you, right, which percentile it is. Now there's some conventions. They do numbers less than, right? Because your value itself is 1, right? So suppose 100 people take a test, right? You're in fifth, and let's say yours is the 15th highest. Well, you're the 15th lowest score, right? Notice that 14% are below and 84% are above, right? If it's 100 test takers. When you have a large set of data, the fact that a particular set of data is one data piece doesn't really matter. So, but just to be sure, right, you say the percentile values isn't the number less than or equal to X is less than X, right? So this would be the proportion of values less than a particular piece of data, right, as a decimal, and then you multiply it by 100 to get the percentage. The formula is fairly straightforward. Hopefully you have some intuition for this formula, right? Questions on this formula. Do we have the intuition, right, that this is the ratio, right? And then we'll just kind of see it, right? Let's do an example, all right? We're here, sure. Right, remember all these are posted online. So you scored 77, right? This is you. So what's the formula, right? You can think of it as multiplying by 100 or just converting the decimal to a percentage. Either way, it's fine, right? So if you scored 77%, how many test scores did you score better than? 3 out of a total of 10. So it's pretty easy to see. 3 out of 10, right, scored worse than you. 3/10 is 0.3, right? You can either think of the 0.3 becomes 30% by multiplying by 100, or you're just converting it from a decimal to a percent, right? This is your percentile because you're saying I did better than 30% of the people taking the same test, right? Another way, and the way you could write this, right, as an expression in one thing is that P30 equals 77. You can read this as the 30th percentile is 77. Questions? P30, yes. That means the score at the 30th percentile is 77. Yes. Yeah. All right, let's keep going. So I want you to notice something here, right? We here calculated a test score, right, which is a particular data value, right? And we use that to calculate a percentile, right? The fact that we did this procedure and that it exists and that it begs the question of another procedure to do something. Is there a procedure to do something else? What is that something else? We had one thing that we knew and we found out something else. Hint, I use an arrow in this diagram that I just drew. Well, that's this particular, I'm thinking more meta, right? I found out how to take my test score of 77 and convert it to a percentile. Gave you a procedure for doing that. So I can calculate a particular data value and find its percentile. What else might you be expected to do? It's much more straightforward than that. Convert what to what? Well, we already did that. This is something you got. Okay, I'll give it to you, and then you can think about this. Right? You know how to assemble a refrigerator. You should also know how to take it apart. So, this is the diagram. Right? And this is what we're going to be doing a lot in class. Right? Given one measure, given X, we should be able to calculate Y. Right? In this class. Also, you should know how to do the opposite. Given Y, how do I get X? Right? So, it begs this question. This is something that we're going to be doing a lot of, right? Later on, right? Notice we only did one way for that, but I could have asked, right? Given a particular z-score, how do you find the original piece of data, right? We're not doing that, but we're doing that with percentile. So I could have just easily asked, what is P40? What score is at the 40th percentile, right? Or the 45th? Does everyone see that? Anytime and this is the meta stuff that I'm trying to help you think about. This helps you organize your thoughts in this class, right? Anytime there, I'm going to teach you almost anytime I'm going to teach you a procedure how to find y given x, you're going to have to figure out how do I get x given y, all right? And here's the procedure. So here's the notation. Some of these are pretty straightforward. N is just the number of the size of the data set, as it always has been. K is the percentile I'm interested in. L is the locator that gives me the position of a score. So for example, if L was equal to 1, it would be the lowest score, right? If L was 20, it would be the 20th lowest score, right? And PK, right, is the percentile that's a particular score, right? So this is what we know. So we start with N and K, right? And we are asking, what is PK? The formula you use is you need to find L, right? That's K divided by 100, right? Because that gives you as the proportion, right? That's a percentage as a proportion, as a decimal, right? You'll see how this works, right? You multiply this by N, you will get L, except not really. Because most of the time you will not get a whole number, right? You'll see the intuition for this, right? When we do the example. If L is not a whole number, you simply just round up. So you always round up. Notice you don't round down like that. That happens sometimes. This makes sense, right? Because remember, the percentile is this formula right here is just K percent of N. That's the percentage we want lower than it, right? So if you find this and you find that the 15.3 is your calculated L, well then, if you round L down to 15, right, that percentage will be, that amount of percentage will be less than it. The problem is when it's exactly a whole number, right? There's a value exactly 30% of the way through the data set, for example. Well, you want 30% to be less than it. If you went up one more, right, that wouldn't quite work. So you want to go right in between the data sets. And I'll kind of show you how this works. All right, so first, right, that gives, and then once you have the position, you just have to find the corresponding number to that position. This might be confusing, but once you see the procedure, it's not that bad. It will make a lot more sense, right? So first thing is your data should be ranked in order, right? Otherwise, you can't really use the locator. So you want to rank it lowest to highest. That would take a little bit of time. I'm going to pre-do that for you. So that is 0, 45, 60, Okay. So first, we want to find the 50th percentile. So we're asking P50 is what? What number has exactly 50% of the values beneath it? And here's 10. So you simply use the formula. Formula being $50 divided by 100, that's 0.5, right? Or 1/2. Half of 10 is 5, right? That's easy. Just notice that this isn't much. All I'm asking, 5, this form, you don't even need to use this formula, right? This is just k% of 10. And 50% of 10, we all know is 5. Don't overcomplicate this. Do we understand how we all computed 5, everybody? 50. So I want the 50th percentile, right? So I want to find 50% of 50% of my way through the data, right? How much data is there? Well, there's 10, so that's 5. That's the intuitive way. If you want to just memorize the formula, that's fine, but it's good to understand where it comes from. Okay, so then we want to look at the procedure. So notice, then we have to ask, is L a whole number? And in this case, the answer is, notice, okay, so this is the first data, second, third, fourth, fifth, and sixth, right? Since it's a whole number, right, if I chose the 5th piece of data, only 4 pieces are less than it, right? So that's not really the 50th percentile, because you want to say, you want 50th to be less than that number, right? So the best way to do it is to find this spot right here, right? Notice that splits it into 50% to the left, 50% to the right. So how do you do that? So when you have a whole number, you count in 5. You add the next piece of data, and you divide by 2. You basically average them. Okay, questions? What? There is. You're going to do it. It's asking, what is P 25? Why don't you guys try this, right? It won't let me write it for some reason. And then I will go over it, right? But I want you guys to try this and work with each other, talk to each other, all right? All the same procedure, but it might be a little bit different because remember, there's slightly different things you do if you get a whole number or not. Yes. Yes. I calculated L, right? And I got 5, right? But, right, if that number, let's say I got 5.1, right? Then if I round down, I know that 5, the 5th value is lower than the imaginary 5.1's value, right? So then I could easily go with rounding down, right? But I'm exactly here, there's actually 4 values less than it. So what you need to do is if you get a whole number, right, if you get something that's exact, you want to average it with the number that comes right next to it. Then you get something that cuts off half of the values to the left, right? Because it's between those 2 values. Does that answer your question? Yes, right. So that is and just looking back at the procedure, I ended up having to do 3A, right? Just a hint, the next problem will have you do 3B so you can get an experience of doing both of them. All right, everyone understand what's expected? All right, let's try to do this and not take more than 1 or 2 minutes. Yeah, roughly speaking, yeah. But don't rely on it to be easy fractions because I could just as easily ask P37, right? Okay, so let's use the formula. K divided by 100, right? times n. So that is 25 for 100, which is 1/4, right? Times n, which is 10. So you're seeing, yeah, I want something that's a decimal, that's 1/4. So I want something where 1/4 of the values are less than, right? Well, what's 1/4 of 10? 2.5, right? So then you just follow the procedure. You just round up to the next whole number. So that 10 becomes 3. Then you count in 1, 2, 3. 60. Yes, sorry. You always round up because I want 25% of my data to be less than it, right? 25 is 2.5, right? If I rounded down, I'd have a little bit less than 25%, right? So you want to round up. Yes. Because you want in that case, we wanted 50% to be less than the data, right? Exactly 50% of the way through was a piece of data, right? So so that data actually has 40% be less than it, right? So you have to move up a little bit, and you don't want to move all the way up to the next piece of data, right? So you go halfway in between. Here, right, we're at 2.5, so my thing is already like roughly here. So it's quite easy for me to make sure that I have 25% less than it. If I'm at the 30th, you can imagine the more pieces of data, right? Like the less the A and B difference would make, right? If I have thousands of pieces of data, it's not likely to be different by doing that. Okay. Questions? Okay. So you could divide all of your data into 100 pieces, right? That's what percentiles do, but that's a lot of information. So a more convenient one is divide into quartiles, right? So that's really dividing it into 4 pieces, right? So you divide your data into the 4 pieces that aren't equally long, but each of them have 1/4 of your data, right? So the value that cuts 1/4, the first quarter from your second quarter, that's called Q1, right? It is, notice, the same thing as P25. It separates 75% of your data from 25% of your data. Q2, which we rarely will use because it's the same thing as your median, right? That separates 50 from 50. And Q3 is the same thing as P75. Notice that Q1 is the center of the smaller half of your data, and Q3 is the center of your larger half, right? So it's kind of the median. Q1 is the median of your lower half, and Q3 is the median of your higher half. Okay, now, right, last chapter was centers of measures of variation. We're now adding a new measure of variation. The one of these that you're really going to use much, these bottom 3, you can put them in your notes, but these are rarely used. This one is important, right? This is called your interquartile range. So it's basically, how do we get a range for a set of data? You subtract the largest piece of data from the smallest piece of your data, right? Well, the interquartile range does the same thing, except it does Q3 minus Q1. Notice this has one advantage over a regular range, is that this is more outlier resistant, right? Because your outliers will be numbers that are either at the extreme left of your data or the extreme right. This thing kind of cuts it out, right? So imagine this set of data. So the range for this data is 104, right? But that's not a good way of expressing the true variation of this data, right? Because notice all of this data is bunched up around the 190 area except for one, right? But notice 95 is our median, right? This is Q1. This is Q3. Our IQR is only 10. The IQR is oftentimes better measurement than the entire range because it tells you where, right, between Q1 and Q3 is roughly 50% of your data, right? That is some, so it tells you where's most of the middle, where's the middle part of my data, as opposed to where's all of my data, which includes values that might be very extreme and unrepresentative. Are we able to see the advantage of the IQR over the range? Questions here. I know this is a lot. You don't really need to work. These other ones you just calculate. These other ones, so the semi-quartile range is half of that. The mid-quartile range is like the number that's in the middle between Q1 and Q3 number-wise, not data-wise. The 90-10 is just telling you where 80% of your data, the middle 80% is. I don't think I have any questions asking about, but these are just things that exist. You could create something, you could create the 199 range or the 298 if for some reason you wanted to, right? But kind of serve the same purpose. The Q1 and stuff, that is the most common one, right? So you can tell me, right? Here's my data. Let's say I divide my data into 4 boxes, each with 25%, right? Well, here's your min. Here's Q1. Here's your median. Here's Q3. And here's your max, right? Notice each of these kind of define the edges of 1/4 of your data, right? So that's what the 5-number summary is. So if I ever ask for a 5-number summary, you want to include your minimum, which technically is Q0, right? But that's a weird thing to say, right? Q1, then of course you want to include your second quartile, which no one almost ever says. They just call this the median. Q3 and the maximum, which I guess technically is Q4. So it's really just giving the quartiles of your data. So 5-number summary. The lowest value, the highest value, the middle value, and then roughly speaking, the middle of the left half and the middle of the right half. A box plot is simply a diagram, and I'll show you how to make it with your calculator. We'll also do it by hand, that represents all of this. So you have some number line, right? This is what your box plot will look like. You find out where Q1 is. Notice I intentionally drew it so it's not symmetric, because it doesn't have to be, right? It's not saying that these are 25% of the way through the range. It's 25% of the way through the data, right? So I could have this set of data being more clumped closely together than this part, right? Each of those boxes has 25% of the data, but right, they might be in different parts, and you'll see that, right? What you want it to do is to be to scale. All right, we ready to see? We're going to do an example, right? And then this will help us. So these are different data speeds for 50, right? Here, notice n is 50. There are 50 pieces of data there, right? 5 rows of 10 each, right? And they're arranged. This is how fast people are downloading when they're at the airport, like on their phone waiting for, right? So somebody is downloading, and I think I've been this person at 0.5 megabits per second, and then someone's doing 77.8, right? That's the fastest. Okay, so if there are 50 pieces of data, the middle, would it be the 25th, the 26th, or right in between those two? So let's just count. This is 10, 20, 23, 24, or sorry, 21, 22, 23, 24, 25, and 26, right? So that is where our middle value is. So first we can easily see our min. So easy, it's first the easiest is to see is your min and your max. And then the median is halfway between those two. You do that, you will get 13.9 is exactly in between those two. So that is your median, which is also technically Q2, right? And then you just kind of find the median of both halves of your data set. So the left side would be these 25 values here. The middle of the 25 would be the 13th value, correct? So that's this right here. So that's Q1. Then you go to the 13th in the other way. That would get you your, so 1 row, 2 rows, 1. Let's see, so 13. This is 10, 11, 12, 13. So that's my 5-number summary. Then your box plot, you just plot those numbers like on a number line, right? That's correctly scaled. So notice what's nice about a box plot is you can see if your data is skewed or symmetric. This data, right, has a very long tail on which end? The right end has a long tail, right? So that, notice 25% of my data is in this area, this area, this area, and this area. So that final 25% is spread out, right? So this shows us that our data is skewed to the left or the right. Right, so this tells us, right, as we'll find out in this next one, that this data is skewed right. So it can help you with that. One thing that students, I'm going to give this, I don't know why I didn't do it before. So this data is not skewed, but there are two things that aren't skewed, right? Normal, which looks like the histogram looks like this, or uniform, where the histogram, right, is kind of flat. This one right here, is this normal or uniform? It's not clear, right? This is uniform. Because notice, right, if you divide into like a normal curve into four things horizontally, most of the area is in the middle, right? In a normal curve, it is more scrunched up in the middle. It's symmetric, but it's more scrunched up in the middle. Here, each like quarter box is roughly the same. So this is uniform. Normal would look more like this. Not quite in the middle. This is probably a little bit over exaggerated, right? But notice, right, the data gets more spread out the further away you get from the center. So 50% of your data is squished together. The other 50% on the more extremes is more spread out. So this is normal. This is uniform. So I think I showed you how to do a box plot by hand, right? Let's show you how to do it on the calculator. So let's all get out our calculators. So here's the box plot. Outlier, right? Outlier is a value that's far away from the rest of your data, right? But that brings the question, how far? So if a data is more than 1.5 interquartile ranges, right? If it's either 1.5, here's a different one, right? If it's 1.5 above Q3 or 1.5 below Q1, it's considered an outlier. So notice that the interquartile range is not directly given by your calculator, but you can easily find it, right? So for example, here IQR is 21 minus 7.9. And that's 13.6. So if I took Q3, add 1.5 times so anything higher than 41.9 would be considered an outlier. So our maximum here is definitely an example of an outlier. You can do the same thing for outliers on the left side. Instead of using Q3, you use Q1, and instead of adding this, right, because that would put it to the right, you'd want to subtract it. Questions? All right, so this is everything that you need to know for these celebrations. There's a long homework assignment. You better get on it now, and there's also the practice celebration. We have about 10 minutes left, right? So now might be a good time to go over the practice celebration, see if there's anything you want to ask me about. I will give you guys maybe like 5 minutes to look through it. Maybe in the last 5 minutes, I will answer one of the questions you guys have about the practice celebration, okay? So kind of look over that, see if there's anything you want to ask about before you leave today, all right?